Start this video with the challenge problem from the last video. We've got an open top cart rolling along a level frictionless surface. We've got a downpour. We want to know what's going to happen to the speed of the cart. Well, we know it's open top. The rain's going to fall in. Just like that. Raining. It's going into the cart. And now, what's going to happen to the speed of the cart? Well, you can think of every one of those raindrops as individual collisions. We've got collisions. We're going to take momentum. We know our initial momentum is going to equal our final momentum. Our initial momentum is going to be the mass of the cart times the velocity of the cart. And our final momentum, we're increasing with the mass of the rain. So we've got the mass of the cart plus the mass of the rain times some final velocity. Well, we see our mass is going to go up. If our mass is going up, to keep the same value as this, our velocity has to go down. Now we just need to look at these answers. A and B both have the conservation of energy. We're looking at collisions. We're using our argument with momentum. So that means C is the correct answer. D would be if we're looking at work. These raindrops aren't going to be doing any work on the cart because we know work is FD cosine of theta. They're falling perpendicular to the cart at a 90-degree angle. Cosine of 90 is 0. So this one is true if you're looking at it in the context of what is the work the raindrops do on the cart. But here, C is the answer. In this video, we're going to be coming back to the conservation of momentum, but we're going to be doing it in a little bit different way. So we know that momentum is conserved within collisions. That's where we most like to use it, as you saw frequently in the last video. But what we need to look at further is that it is conserved in each dimension. So it is conserved in the x direction and in the y direction. That means the sum of our initial momentum in the x direction equals the sum of our final momentum in the x direction, and the same holds for the y direction. So with that knowledge, we can now begin to look at two-dimensional collisions, and that's often more realistic. So this first problem, we have a pretty simple collision. These are two objects with the same mass, same initial velocity, and they're moving towards each other at the same angle before they collide at this point here. And we want to know the velocity of the collision, their velocity after the collision. And we know that they stick together, so they're going to become one object. So if we were to decompose this, you would see that this object up here has initial velocity in the y direction like that. This object has an initial velocity in the y direction of that. And the initial velocities in the y direction are going to sum to 0, so we're just focusing on the x direction. And because of that, you could say that their motion after the collision is going to be just along the x-axis. So we could say the sum of their initial momentum in the x direction is going to equal the sum of their final momentum in the x direction. And we can decompose that to say we have m v naught cosine of 60 plus another one, so we have 2 because we have two objects, and that is going to be equal to twice the mass now because they stick together times some final velocity v sub f. Right, and both of these objects have a positive component of the x momentum because they're moving in the positive direction, and they're both moving in the same x direction. So we can immediately divide by 2m, and we know the cosine of 60 is 1/2, and we can say v naught divided by 2, or times 1/2, equals our final velocity, and that means B is the answer. It's a little bit of a tricky problem, especially for an introductory physics video, but what we have is a stationary object that is going to explode and break into 3 pieces of masses m, and 3m. Our 2 pieces of mass m are going to move off at right angles to each other with the same magnitude of momentum, mv, as shown. We want the magnitude and direction of the velocity of our piece with mass 3m. So notice that this object is initially stationary, and by the way, I really encourage you to pause this video and give it a try. So because our object is initially stationary, its initial momentum is going to equal 0, which equals its final momentum. Remember, this sigma just means the sum of. And in order for that to happen, this third m needs to have components of momentum that are equal in magnitude in opposite direction. So it's going to be in this direction, but I can just draw it kind of like that. We know it's going to go in that direction, so we can easily rule out options A and C. And now on the AP exam, you would have a 50-50 chance, which is better than a 25% chance of getting it right, even if you didn't know what to do next. So we know that the components need to be in opposite directions to our given components, and we can sum those to get our total components of momentum, or our total momentum. So we can sum this using the Pythagorean theorem, which basically says that a squared plus b squared is going to equal c squared. Let this be our a, let this be our b, and this will be our c. So we can solve for c with the square root of a squared plus b squared, and that would give us this, which we can simplify to 2 square roots of m, or no, that's backwards. This will equal mv square root of 2. Alright, so that is going to be the magnitude of momentum of this 3m, and we know that our summation of momentum 1, or A, plus B has got to equal C. Because remember, C would be negative if we were going to set this equal to 0 right here, because it's completely in the opposite direction of A and B. So that means that our square root of 2mv, because that's what we just summed, A and B, is going to be equal to the mass of our third piece, 3m, times its velocity. So we can cancel our m's and see that our velocity of 3m is going to equal the square root of 2v divided by 3. Option D. Will be the last practice problem for this video. So we have a two-dimensional collision between 2 balls on a frictionless horizontal tabletop. Ball X is initially moving to the right towards ball Y at 10 meters per second. They elastically collide. Remember, at the beginning of the last video, we learned that means that kinetic energy would be conserved. And the balls are identical, so we can assume that means they have the same mass. And then after the collision, ball X moves off at 6 meters per second along a path at 53 degrees to its initial path. We want to know which of the following diagrams could represent the motion of ball Y after the collision. We've got a collision, of course. We're going to be using conservation of momentum. So our initial momentum is just due to ball X, and it is just horizontal. So that means when we sum the momenta of the 2 balls after the collision, we have to have a y component of 0 because we have no initial y component. So in that case, that means our y component of x has to equal our y component of y. So that means our mass times our velocity of 6 meters per second And then we're in the y direction, so we'll be using the sine of 53 degrees is going to be equal to the mass of ball y times an unknown velocity times the sine of an unknown angle. But we know our masses cancel out. And actually, I want to use different variables here. We're just going to call this our unknown velocity A and our unknown angle theta, not alpha. Now we know our x components of the two have to equal 10 meters per second. So, because that's our initial one, so initially we've got 10m, and that has to equal, we're looking at our horizontal direction, that needs to equal 6 meters per second. We don't really need to be worrying about using our units here, times the cosine of 53 degrees plus ma cosine of our unknown angle theta. Those are the equations because our initial momentum in the horizontal direction is 10m. So when we look at our horizontal direction here, that also has to equal 10m. However, we know our m's all cancel, so they have to equal 10. You could do some very interesting substitution here, or we could just look at our options and see if we could rule one out. So anyway, let's do it the little bit more tricky way in case you have this as a free response question or something like it as a free response question. So we know 10 is going to equal 6 cosine of 53 plus a cosine of theta. Scroll down here so we have a little bit more room to work. We will be going back to the question. What we have now is two equations with two unknowns. We gotta solve for our unknowns. So we're going to be using approximations to 2 decimal places. And first we're going to start right here with our 6 sine of 53. And that will give us about 4.79 equals a sine of theta. Remember, because our y components have to sum to 0, so that means our final x component, our final y component of ball x has to equal our final y component of ball y. We can go back up here. We know 6 sine of 53 has got to equal a, our velocity of ball y, plus the sine of whatever angle it follows. And then in our horizontal direction, we know that 10, because remember we can get rid of all the m's because the m's are equal and they're not sticking together at all. That has to equal 10, so we've got the 6 cosine of 53 here, plus our velocity times whatever angle ball y will follow. Alright, so now I'm going to take 10 and I'm going to subtract 6 cosine of 53. And that gives 6.39 equals a cosine of theta. Alright, now we can say that a is going to equal 4.79 divided by our sine of theta. And now I'm going to substitute that in here, so we have 6.39 is going to equal 4.79 divided by, actually we're going to have cosine divided by sine, so I could just say cotangent of theta. Actually, you know what, let's do it the other way around so we can deal with tangent instead of cotangent. Let's say a equals 6.39 over cosine theta. And then we can just do this. Alright, so we can do some division. 4.79 divided by 6.39. And now you can take the arctangent of that to solve for theta. And you're going to get that theta approximates to 36.9 degrees, or let's just round up to 37 degrees. Substitute that in to solve for A. So you take 6.39 divided by the cosine of that answer, and you'll get that A approximates to 8 meters per second. So let's go back up here. We need 8 meters per second at 37 degrees. That gives us C. Alright, now I just want to really quickly go over how by the process of elimination you could quickly get that answer on a multiple choice test. Firstly, you can obviously rule out A because we know we need our y components to sum to 0. So we need something down here that would equal this here. Immediately rule out A. We look at B. We see we have a smaller angle than 53, so that means we would need a bigger velocity so that the sine of that angle would contradict 6 sine of 53, but we have a smaller velocity. You can see 4 sine of 37 is going to be less than 6 sine of 53. We look at C, we see we've got that small angle, so we need a larger velocity than 6 meters per second. We're given 8. That might work. We look at D, we've got an angle equal to 53. So if we were going to do that, you would want to have 6 meters per second sine of 53 because these would be equal and opposite. We have 8, so this is going to give too large of a negative y component. And then we know C is the correct answer. Challenge problem for this video, you can find the solution on my Instagram page linked in the description shortly after the release of this video, or you can watch it at the beginning of the next one. I know we haven't covered impulse yet, but for now I really want you to use your intuitions to see if you can solve this problem.